Yeah. So good morning, everyone. Welcome to the weekly seminar session. So this time we have the privilege to have Professor Sili Deng at MIT to give us talk about her research. So just a brief introduction of Sili. So Dr. Deng obtained her undergrad degree at Tsinghua University, and then she went on to Princeton for her PhD studies. And then after she graduated, got her PhD degree, she went on to conduct a postdoc research at Stanford University. So now she's assistant professor at MIT. And then she will give us a talk about her work on the new roles and tools for combustion in battery research. And Sili has already won the Bernard Lewis Fellowship from the Combustion Institute and the NSF Career Award. So without further ado, let's welcome Dr. Deng.
Thank you very much, Yang and David, for inviting me for this seminar and giving me this great opportunity to interact with the faculty and students in the department. Before I set up this Zoom meeting, I noticed that there seemed to be some latency from this internet connection. So feel free to let me know if the internet is broken so I can catch that and restart. So like Yang mentioned, we had an overlap in undergrad, and that's where I developed my interest for combustion. And then I carried on for a PhD study at Princeton, and the research was mainly focusing on the chemical kinetics and flame dynamics of combustion phenomena. The fuel at that time that we were interested in were fossil fuels, and we are interested in developing safety and more controllable combustion processes for aviation and propulsion applications. Nowadays, since we're talking about trying to cut to mitigate emissions from the combustion of fossil fuels, this kept me thinking, what can I do as a combustion scientist? What role can I play during this transition from the burning of fossil fuels to fully renewables? This entire spectrum of questions that I can be part of. One thing is that I can continue to work on combustion and maybe even developing new alternative fuels that are carbon neutral, or I can use combustion as a way to manufacture key materials to harvest renewable energy and do energy storage. So that motivated half of the research I'm going to talk about today is the new roles of combustion in battery research. On the other hand, combustion is a technology to turn the chemical energy embedded in the chemical bonds of materials into thermal energy. So by definition, it does not assume what kind of material we are burning or fuel we are burning. This is a coupling between the chemistry and fluid mechanics. So I was thinking, now what else in battery research would leverage my knowledge in combustion? One of the key issues that I identify is the thermal runaway of batteries, which results in the explosion of battery packs. So the second half of the talk, I will introduce some new data-driven tools that our group has developed.
I'm sorry, madam.
Yeah.
But your slides are not moving.
Yeah, I'm giving the introduction. Yeah. So for the second half, I will talk about some new tools we developed in the past few years to enable the research for this cross-disciplinary endeavor. So like I briefly mentioned, I hope the slides is advancing right now. This is that's a quick summary of my PhD research working on the combustion of fossil fuels, candle, for example, because I want to utilize that to motivate the soot research. So essentially, when we talk about combustion, we also have the combustion byproduct. Some of them are undesired. For example, the soot particles, or someone else would call it carbon black, etc. I believe a larger number of students that is in the attendance today has been working with Yang and also dim beeswax. So you guys are familiar with this terminology of flame generated particles, etc. Essentially, it is the particle comes from the gas phase reactants, and via a series of chemical and physical processes, primary particles would get formed, and then during the collision and growth of these particles, we will have different morphology of the end particles, secondary particles. For example, for soot, depending on whether we can fully oxidize it or not, we will have smoke generated out of this process. So in terms of combustion process, we want to minimize the generation of soot. First, to enhance the combustion efficiency. Second is try to mitigate this emission. However, we are engineers. We always think how we can turn the disadvantage to our advantages. So let's take a step back and think about the whole entire process. It's basically a material synthesis process where we input precursors, in this case would be the vapor of the candle, and then via the flame, which act as a reactor, and we can generate solid particles, which is the undesired product. But can we turn this into something more controllable and useful? I believe some of you might find this similar to Yang's research, is that we want to utilize this type of process to synthesize particles, synthesize nano or micron particles for energy storage, for energy conversion, sensing, etc. So this is an illustration about how industrial-wise are synthesizing carbon black that has been used for the reinforcement of tires. And I will not dive too deep into this. And the potential application our group is targeting at is the lithium-ion battery market, driven by the needs of transportation electrification and grid energy storage. The demand for lithium-ion batteries has increased dramatically over the past decades. And it is depending on where you get the sources, but there is a consensus that this demand would get even 10 times more in the next decade. So a very natural question we ask about is that, okay, given the large amount of need of this lithium-ion battery, how can we build this infrastructure in a very large scale? Then the cost of the infrastructure is a very important component to think of. So imagine yourself getting an electric vehicle. What would be the things that you have in mind to make this purchase decision? Then, of course, the upfront cost. And nowadays, for an electric vehicle, the biggest cost comes from the battery packs, right? After you purchase it, then you care about, for single charge, how long my trip can last. That depends on the energy density of the battery. And after the energy is consumed, how long does it take for me to recharge it? That depends on how fast you can charge the batteries. That's a charging rate. And ultimately, right, nowadays the electric vehicles is more expensive than the traditional IC engines. But why people still want to buy it? The first one is we care about emission. The second one is that we think in the longer lifetime, due to the lower cost in fuel, we can do this break even. So definitely the lifetime of the battery is a very big factor to be taken into consideration. So we need to, whenever we talk about the material, we talk about battery technology, we should give these 4 things considerations and keep them in mind. So speaking of the cost for a battery system, there are several components listed in this pie chart, but depending on its chemistry, but roughly 40% to 60% of the cost could come from the cathode material, which is general in the current lithium-ion battery market. Currently, these cathode materials are mainly multi-component metal oxides. And for the demonstration that I'm going to talk about today, we're interested in the NCM, which is a widely used batteries in vehicles, in electric vehicles. And we want to demonstrate how the combustion-inspired synthesis method could help us lower the cost of the synthesis of NCM 811 materials. So before we dive into the technology that I'm going to focus on, I want to briefly introduce to you the current technology in the industry that is used to synthesize cathode materials for lithium batteries. This process is called co-precipitation. So by its name, you can think about it's a precipitation process, meaning that particles need to come out of the liquid. So this is the flow chart of the entire battery cathode material synthesis process. It can be broken into 2 components, the precursor production part and the lithiation. So in the precursor production part, all the transition metal oxide precursors in the form of salt will get dissolved, and then in the reactor, by controlling the pH, we can do this co-precipitation process, and then we filter out the particles and deal with the waste solution, and then we try to dry the particles, separate them, and then it's the next step where lithium source with the salt, in the form of lithium salt will get mixed with this residuals from the previous step. So the second step is the solid phase mixing, which, as you could imagine, the mixing and the diffusion could be very slow. That is why a long time thermal treatment in the annealing process is needed to enhance the mixing of all the transition metals to result in uniformly distributed elements. And then it's the particle technology, then we do the agglomeration and form the cathode powder, which are combined with other materials to form the batteries. So the takeaway from this technology is that the previous step in the precursors generation step is that via this liquid phase mixing, we can have homogeneous element distribution except lithium, and this process can control the particle size pretty well. But most of the time, this batch-based process is quite time-consuming. It's more than 10 hours. So it's very difficult to integrate this process with the later on the lithiation and thermal treatment. And the lithiation process is definitely needed to introduce lithium. And because of this solid phase mixing, the uniformity can be achieved only after relatively long time of annealing. To give you an idea, it's about 700 to 800 Celsius for, it can be as long as overnight, right? So the entire process for a single batch, we are talking about the order of days. So this entire process is time consuming, energy intensive, and as you could imagine, all of this would add to the manufacturing cost of lithium batteries. So in order to be able to scale up the production and meet the increasing demand of lithium batteries, the following 3 aspects are taken into consideration, all with the hope that we can reduce the cost of synthesis. And different method has been proposed for you can think about the wet chemistry based, or as some of you are familiar with, is the spray pyrolysis based, meaning that we leverage the heat generated by the flame or do the electric heating and try to do the pyrolysis from the liquid phase precursors into particles. And this technology has been demonstrated in lab for a large variety of lithium-ion battery cathode materials. And particularly in our lab, we want to take this one step further and try to demonstrate how we can really shorten the entire synthesis time to achieve desired performance with acceptable cost. So this slide will give you a brief introduction about the experimental system that we built in our lab. We call it a flame-assisted spray pyrolysis, meaning that there are actually two heating elements. So the precursors, I hope you could see the laser pointer here. So different from the co-precipitation method, we have the solutions with all the important or active materials in the lithium-ion battery cathode materials. So including lithium, we also have the other transition metal oxide salt, all dissolved in solutions. And via this ultrasonic nebulizer, we can introduce droplets into these two heating sections. That's why it's called a flame-assisted spray pyrolysis, that we have a preheating section that does not contain flame, that give us a more controllable and especially the gradients controllable heating of this precursor. And then we have a cold flow burner where we have this flame to produce both the high temperature as well as the oxidative environment for the decomposition of the precursors. And after these two processes, we can get solid particles, which is gathered by the filter. And then we take the materials and follow the industrial procedure to do the post-treatment for a long time. So the practice right now here is try to compare this precursor generation part with co-precipitation method and demonstrate this method indeed can result in the desired product. And as a case of demonstration, we picked NCM 811 because it is the N stands for nickel, and thermodynamically, this type of composition will give us a high theoretical capacity due to the high nickel composition. However, in industry, this has been very difficult to synthesize. Even in the literature, when people try to use spray pyrolysis method for this high nickel component, it's quite difficult to do. And what do I mean by really good performance is that if we can achieve a specific capacity, about 200 milliamp hour per gram, that is really a benchmark or milestone to achieve. So in the following, I'm going to introduce some technical details about this work, and it's mainly done by my postdoc, Dr. Janan Zhang. So we are interested in seeing how important it is to control the process, or put it in another way. Does it mean that if you have a setup like this, you can just dump as much as materials and as fast as possible to increase the throughput? And does that influence the performance? And what is the role of combustion or controlling the temperature in controlling the morphology of and the performance of the materials? So the answer is yes, it is very, very important to control the entire physical process, especially the temperature history that the precursor droplet experience to form the particles. So the way we did it was that we can control the temperature in the preheating section. So now this graph shows a sweep of temperatures starting from the room temperature, no heating, to as high as 325 Celsius. And the bottom row demonstrate the TEM images of the end particles. And then you can see indeed the morphology changes a lot. So I'm not sure if things are shown on your end very clearly, so we can focus on this schematics to give you an idea of what happens. So what really happens is that during this, if there's no preheating section, we directly spray things into the flame. We will end up with these broken particles, meaning that they do not have very good integrity and the mechanical strength is weak. So you can imagine after we combine them with other materials, the performance would get impacted. Okay, at a very high temperature of the preheating, we could get some spherical particles, but first the size distribution isn't very uniform. And from the contrast, you could probably also see that the particles is hollow. And somewhere in between, we see this transition from a dense, spherical, relatively uniform particles to the hollow structure, etc. By controlling the preheating of the section, meaning that controlling the temperature history of the particles. So definitely the conclusion here is that the temperature history that the precursor experienced definitely influence the morphology. But does that also translate to the performance? And this is a quick test without going into too much details. Basically, this figures shows how the temperature of the preheating zone influences the efficiency of the charging and discharge of the cathode materials after we assemble everything into coin cell. The coin cell is probably, I'm not sure if you guys still utilize calculators, but if you take that out, that's a coin cell. And the particular size we're synthesizing is a 2032. You can buy it in CVS on the over the counter. You can see how big it is. So we characterize the specific capacity of the battery, the efficiency for the charge and discharge, and we can charge them also at a different rate, how long it would take. So in battery community, when we talk about the C rate is how fast we charge things. So 1 C rate is the rate that you fully charge a battery at 1 hour. So the 0.1 C means that you need 10 hours to charge it. Okay, but normally people utilize a low charge rate to characterize the total capacity of the material and measure the performance at different C's and try to get the retention ratio after like 100 cycles or so. So the take-home message from these figures is that compared to the reported value for the NCM 811, we can achieve comparable high performance, about 200 milliamp hour per gram. And also after 100 cycles, we can keep a retention ratio of about 80%. This all meets the standard set by industry. But we also can see for this particular project, we can see such high performance window is concentrated in between. And the two extreme cases that are presented indeed did not give us acceptable performance. So this brings us to what can we do, right? So I just demonstrated, yeah, we can replace the current co-precipitation method with this flame assisted spray pyrolysis to quickly synthesize materials of desired morphology and performance. But what is the implication this can bring us? Do we still need to have the same annealing and post-processing procedure as previous? if I may remind you of the need for the annealing for the co-precipitation, is that lithium was added to the system in this solid phase mixing. So you need this very long annealing time for the diffusions to happen. However, in our case, we have already combined lithium into these precursors. So we do not need to have a solid phase mixing. Does it imply that we could do something else to further simplify the process and reduce the cost? Now we think about why we need the annealing. Like I mentioned, we need to achieve certain crystal size, and we need to achieve the uniform distribution of elements. And this can be done basically constrain us into these two corners, right? The industry utilizes this method is that we use relatively low temperature and long time so that the process is slow enough, we can control it. Of course, the downside would be you need a long time, so it's very energy intensive. You need workers to be there, you need things to run for a very, very long time. So we think, okay, now we have already incorporated lithium into the precursors. Can we try this method that we maybe increase the temperature a little bit, but we can significantly reduce the annealing time? And we want to try that idea. And this is what we tried, is that we found that, okay, why in previous study we needed a long synthesis time is that after we synthesize the particles, due to the difference in temperature sensitivity between lithium and other transition metals, lithium actually gets concentrated on the surface of this particle. And this is tested by removing lithium from the solution. You do not have that nanomaterials anymore. So we confirmed that indeed we have this phase segregation where we have lithium enriched at the surface of it. And then you could imagine if it's not uniformly distributed as we supposed to have, then of course we are basically having another solid phase mixing that requires long annealing time for diffusion to happen. So what can we do? We try. The scientific question becomes, is there a way to maintain the uniform mixing of this precursor, even if we spray it into the high temperature region? Okay, so this is the current way that I just introduced. We have this lithium enriched surfaces. And this is some magic we did afterwards, where I will talk about exactly what it is. But you can see from the SEM and TEM, these nanomaterials disappear. And after we also dissolve the particles into acid solutions and try to see if it means that we are losing lithium. The answer is no, the lithium content keeps the same as previous case. So the only explanation would be now our lithium has incorporated into the particles. It has been diffused into and have uniform distribution with the other metal oxides. So the magic we play was to use urea as an additive 1%, 2% by mass into the solutions. We don't need to really go to the details, but this is to demonstrate after we utilize this method, how this end product is sensitive to temperature. Because the whole reason for us to design this process is try to push us to a higher temperature annealing process, such that we have this hope to shrink the annealing time. And the purpose of this slide is try to show you a thermal XRD, meaning that we can do the XRD as we increase the temperature of the environment and see how sensitive the material is to the temperature. The take-home message is that if we have this lithium enriched surface, then the sample will be very, very sensitive to the annealing conditions. You cannot have too low temperature, you cannot have too high temperature. But if for the second case where we add urea, the end product is less sensitive with its peak, meaning that it can withstand a relatively wider range of temperature. So it gave us the hope that we could try a high temperature annealing. And before I dive into the proposed mechanism, why things work, to complete our test, we also did this coin cell performance. And as I indicated in the thermal XRD, you can see that without adding urea, we do see notable difference if we change the annealing temperature for 50 Celsius, for example. You do see the capacity changes a lot. However, for this new material with the urea added in the precursor, afterwards urea is gone, it's decomposed, we do not see differences, giving us hope to expand the annealing temperature region. So I just talked to you that this method works, both worked for the morphology requirement as well as the performance requirement, but we as scientists, we want to understand why it worked. So this is the proposed mechanism. For the NCM precursors, due to the intrinsic difference in diffusivity of the precursors, lithium tend to enrich at the surface, and after the salt gets decomposed, the resultant would also keep the same morphology. That's why we need a longer calcination time for lithium to diffuse back into the layer structure of this transition metal oxide. Whereas when we add urea to the precursor, urea itself is sensitive to temperature. It generates bubbles, which introduces internal motion of inside this droplet to enhance mixing. So you could imagine there are bubbles that act as stirrers, try to enhance the mixing such that we can get uniform distribution for all 4 elements inside this. That is the foundation for the short calcination time needed for the annealing process. And here is the summary of things, right? In the traditional method, after we get the material, we need to do this annealing process. The annealing takes 13 hours in industry. And also the material is so sensitive to this temperature such that you cannot just open the oven and put the particles in. You need to ramp it up from low temperature gradually. So the entire time needed in industry is more than a day, or roughly a day. However, in our case, since our particle is so robust, we can ramp the temperature up to 875 Celsius, and we do not need to have this gradual ramping, and we do not need to cool down slowly. We just take it out and let it cool down in air. So totally it's only 20 minutes. So we have a significant decrease of annealing time, in addition to the 50% of time cut happening during the synthesis of the particles. Quickly, I'm going to show that some further characterizations demonstrated indeed we're gathering the desired crystal structures with uniform distribution of all the elements of interest. Performance-wise, this is not the best performance we get, but because with the traditional method, you cannot get even better performance. So we just pick one case that matches the performance of the without additive case. Both of them, they have comparable performance, but you can look at this, our synthesis time and annealing time, our annealing time is significantly shorter. And compared to the literature, essentially we can achieve comparable performance no matter which wet chemistry method or flame spray pyrolysis method they use. We achieve comparable performance, but we can significantly shrinking the time needed for the particle synthesis. So the partial summary for this first part is that we can really control the entire temperature history that is a precursor experience to form particles. And this turns out to be very important to control the morphology and performance of the battery materials. And with this shortened synthesis time and simple geometry, simple equipment, we do see great potential for the scaling up of this technology to be widely used in the industry. Okay, I just introduced to you about how we can take the knowledge that I accumulated over my years of training as a combustion scientist to change the direction to synthesizing materials. Now I want to mention how about we directly apply our knowledge about combustion onto solving battery safety issues. But maybe we can borrow the tools or get inspired by the tools that is rapidly developing in the machine learning community and try to combine the physics and data-driven modeling approach together to model this very difficult battery fire problem. So as someone trained as a scientist, I do have a deep appreciation of science, and I like the feel of being able to explain what happened. So this is a thing, the machine learning definitely is a very inspiring topic for me, but I always wanted to be able to explain what happened to the models that it gets extracted from machine learning approaches. So my personal take of this would be for black box machine learning, it is definitely a very, very powerful tool to do the regression and to do the pattern recognition from a variety of data for a large amount of data. However, it does not, it is perfect for cases where we do not have a good physical intuition. We do not need to specify any physics prior to that. However, the generality of this approach is very limited. We all know it is a consensus that black box machine learning cannot do extrapolation. It can only do well in the region where you have training data and you have a lot of training data to give you the basis. However, we all learn first principles, governing equations, etc. These are models as well, but they are interpretable, they have physical meanings, and they can be extended even to cases where you do not have a measurement yet. Right? So this motivation for me and for my group is that how can we combine the advantage of these two to develop the so-called physics-informed machine learning for the engineering or scientific problems that we are interested in. Next, I'm going to introduce the framework called chemical reaction neural network developed in my group. And this effort was led by my previous postdoc, Dr. Weiqi Ji. The rationale is like this. When we are dealing with a large scale of chemical kinetic system where we have thousands of species, tens of thousands of reactions, it's impossible to manually propose all the possibilities of the connections, of the pathways, and try to manually fit the kinetic parameters for all of this. We want to leverage the machine learning tools for this large scale optimization. However, we do not want to have black box optimization done by neural networks, for example. We always want to leverage the physical laws such that we can inform the machine learning model, and even better, to achieve a model that is physically interpretable. And the naive idea we have in mind is that how about we inform the structure of this neural network such that all the weights that is in the neural network are physically interpretable, meaning they have physical meanings. In that case, after we get this neural network, we can translate it back to the human readable format and understand the physical insights. And I'm going to demonstrate to you this is doable. So give you a general example of a reaction, A plus B goes to C and D, where the New's coefficients, they are the stoichiometric coefficient. Generally speaking, the chemical system would obey the law of mass action, is that the rate of the reaction depends on the concentration of the reactant to the power of the stoichiometric coefficients, and is proportional to a rate constant. And in a lot of systems, this rate constant is indeed a constant. For other systems, such as the combustion or system that I'm interested in, Arrhenius law is also important, whereas this rate constant is a function of temperature. So that makes sense, is that you need to overcome certain energy barrier for the reactions to happen. So these two laws are generally observable in nature. So they are general enough to be the fundamental physical laws that we want to incorporate, that we want to inform the models. And this is how we did it. Take this example of methane plus oxygen goes to CO2, carbon dioxide, and water. We want to encode this law of mass action into a neural network. So we just express the reaction rate into this format and did a little bit of algebraic manipulation, taking the exponential term is just an equality. And then you can see everything else inside this one becomes a linear combination of terms. So there is a nonlinear operation, but here is a linear operators. And we can explain this into a graph like this. And some of you who might have written work on machine learning or neural network, you can see these are the neurons. These are the output neurons. So the take-home message for this is that we can express the chemical pathway in terms of a neural network. Now, in the neural networks, all the weights, bias, activation energy, etc., have their physical meanings to represent the reaction orders, rate constant, and stoichiometric coefficient. So after you achieve this, after you optimize this neural network, every parameter associated with that would be able to be translated into their physical counterparts. Similarly, we can incorporate Arrhenius law to represent this rate constant term with another neurons. And putting things together, I just mentioned a single reaction, and if you stack all of them together, then you can deal with a mechanism system, right? A reaction system with a large number of reactions. Now the number of hidden nodes will represent the number of reactions, and all these open nodes correspond to the species and temperature. And we utilize that to do a few case studies, and without going too much details because it's not too appealing in terms of the illustration, but it's actually very powerful. So we first tried 5 species, 4 reactions network, and feeding only the concentration, time history into the neural network, let it learn, so it can recover the ground truth perfectly. So this is a learned result, and you can see they all correspond to this mechanism. So we did not tell the neural network this is the template, you try to fit the numbers for that. The neural network itself can tell us what are the pathways, and also can tell us simultaneously what are the kinetic parameters. Similarly, for diesel fuel production, without telling them this, in this case, we will have the temperature dependence on the rate constant. We can almost perfectly, there will be some deviations, but within 1%, to extract the kinetic parameters and pathways out of this training set. Even more complex, I don't even understand this chemistry, but doesn't matter. The neural network can tell us what it is. So this is a biochemistry, which I personally do not understand. It is related to protein kinases, and it is related to cell signaling. And in this case, essentially, you can imagine some of these reactants are catalysts, so they are not consumed or generated. And a lot of times, they do not even have very good balances from the right-hand side and left-hand side, but it does not matter. As long as we have this framework, it can extract the underlying physical mechanism out of this data. You can really unravel the information contained in the data. We further can do this exercise even if we do not provide the full picture of all the species involved, meaning that we can really deal with unknown species. A short description of this would be, we give the system some species, we do not tell it how many species are involved, and they are able to recover. Not only it's the 5 species you provide to me, there needs to be a very important intermediate species that you do not have any measurement of that can make everything happen. So this is beyond regression. This is telling us something new. This is really discovering pathways and unknown species. And then we further applied this method to analyze condensed phase pyrolysis. And the difficulty in this scenario would be, now what we can measure is the overall weight of the system. We do not even know that belongs to certain species. So a lot of them would be pseudo species. We only know what's the original reactant, and we know in the end it becomes gas and some solid residuals. But it can tell us some feasible pathways that implying there are some intermediate species, intermediate pathways to lead us to the final results. These would be the parameters come from derived from the neural network, and all of them would correspond to their physical counterparts. Reading this graph would generate a mechanism like this, giving you the pathways and the kinetic parameters. And using this would be able to help us understand what's going on as temperature increases. This is a total mass, but essentially what is contributing to the mass? What are the residuals? Even we do not have good physical understanding, exactly the name of the product, there are ways to predict what's going on and give us a hint. Okay, this intermediate species could be something. And finally, we are applying this method to tackle battery thermal runaway. So you have read news about this, that about 3-4 years ago, when Samsung really launches, I think it's Galaxy or Note, and you cannot really take your cell phone to the the play, right? Because of the battery safety issues. And recent years, you heard a lot of news about electric vehicles on fire. So battery safety is a big issue, and we want to understand why thermal runaway happens in batteries from the normal operation, why the temperature all of a sudden cannot be well controlled. For a lot of electric vehicles, there is actually thermal management systems to try to cool down the batteries if the temperature is abnormal. But if we could have a model to predict what's happening, we can take precautions ahead of time before the disaster really happens. So in battery fire safety community, people utilize DSC, experiment scanning, differential scanning calorimetry, try to measure the heat release from the battery packs and then try to derive information out of it. Very often it is a manual process. You do the experiment at several heating rates, and then you try to extract information, assuming a lot of things. And we are thinking, can we not assume this? And actually, a lot of assumptions are not physical enough. For example, in order for this method to be used, one has to assume you can see there are 3 peaks. So one has to assume there are 3 independent reactions. However, physically, it is not the truth. We look into the literature for battery materials, it starts as a single material. And if the temperature goes up, the materials start to degrade and to transform into different other materials. So it is not true to assume that these 3 reactions are not related. But currently, if you do not assume that, you cannot do it. So we are wondering if using our CRNN chemical reaction neural network, we can do that. So before I give you this talk, I just asked my student to prepare me 1 slide on the result. So this is work in progress, so please do not distribute it. And we definitely can have even better results. Is that without assuming 3 independent reactions, we can actually come up with another model, assuming this series reactions, step by step, different stages of degradation. And you can see the green curve, which is the CRN model prediction. It matches with experiments very well, no worse than the ones with assumptions. So we hope that with this framework, we can really help the community understanding what's governing the thermal runaway of batteries, and be able to mimic the more realistic scenarios. And with that, I would like to conclude my talk with acknowledgement for the funding agencies. And as I mentioned to you, I was not trained as a material scientist. I basically try to leverage my training in fundamental combustion research and look into different new areas for materials, for energy storage systems. And also, I do think that a lot of the knowledge that we have for chemically reacting flow, it can be related and translated to other research areas. So collaborations are always welcome, and I really appreciate this opportunity to speak to you. Please feel free to ask questions or connect with me afterwards, such that we can discuss research opportunities. Thank you very much.
Thank you, Sili, for your fabulous presentation. So now it's time for questions. Any questions from the audience? So I think some of us typed in. So Shruti, if you're online, maybe you can just directly speak to the microphone.
Dr. Wang, my microphone, is it stable?
Yes, that works.
Okay. So thank you for the amazing talk, Dr. Deng. The first question is, did you find other components other than urea, since you only need to create a bubble inside the particle for lithium to enter inside the particle?
Yeah, maybe I can take it one by one. The quick answer is yes, there will be other materials, and even if they do not generate bubble, they can have other mechanisms. For example, have very viscous ones that you can basically you just freeze it, right? So you would not have lighter species going out too fast. There are many ways to do it. So the main concerns that we took into consideration is urea is very cheap. For a larger application, you definitely want to control every single component as much as possible.
Just a second question. Would you need to change your ML model if the reaction equation is different? Let's say your number of products and reactants change. Since you specifically mentioned for one equation, so how would that model change, or you could still use the same model for other reactions?
Great, that's a great question. So the quick answer is, if you do not violate these two fundamental laws, then we do not need to change. So if all the reaction you have in mind follows law of mass action, then we do not need to change it. It does not matter how many products or species or reactants are in this equation. For example, if you guys can still see my laser pointer for the summary graph, this is just for the condensed matter, but it's the same thing. You can see for this reaction, all of them can contribute to this reaction. Meaning that if you have 10 species overall, not all of them all react at once, but if you want them to be, this network can still make it happen. And that is why, if we go back to the one of the example, okay, here is a perfect example. Because these reactions only consider, this ground truth only have like 3 reactants. A lot of these matrix are 0. It's sparse, meaning that not all of them are connected. But if you have a reaction that have 3 reactants and 6 products, then this matrix will have more non-zero components.
Thank you so much.
So the next question is from Sujit. So Sujit, do you want to talk about your question?
Yeah, sure. So thanks, first of all. I think it's definitely very interesting. So my question was, so did you see the effect of size or morphology of the cathode materials, like whether it is aggregate or spherical or hollow, on the energy or power density, or even the cyclical stability of the material?
Yeah, the quick answer is yes, and it's not only our group. The literature has a lot of discussions on this, but might not be consensus. So definitely the morphology is a very, very important thing to be considered. And in industry, one thing on top of this would be the cap density. So this means that, yes, you can have a very good powder, but at the end of the day, to increase in the total capacity of the pack, you need to be able to pack as much as active material as possible to your battery. So the mechanical strength also matters. And whether you can pack them dense enough also matters. But if you also do not want to make it too big, because when the particles are too big, the intercalation during the operation, the diffusion of lithium-ion into the crystals would be very, very difficult. So the charging behavior would be bad. So the quick answer is this is a wonderful question. It's a question shared by the entire community, and morphology definitely matters on the performance.
Thank you.
Yeah. Next question is from Shaunas. So do you want to raise your question?
Yeah. So, hello, can you hear me?
Yeah.
Yes.
Okay. So actually, your research is actually really cool to me, because that's what we do in our lab here. We make nanoparticles, but we use the traditional method, like, the sol gel, precipitation, all that. So I noticed one part that was particularly interesting to me was that you talked about how you have that lithium shell that sort of forms,
Yeah.
right? And in our case, actually, that's actually a process that we think might be useful because we make multi-layered nouns particles. So we have a core and then a different material for a shell.
Yeah.
So do you think that's possible to make with a one-step process? So instead of annealing out the lithium shell or using urea, we in one step try to make both a core and a shell in one go.
I think it's possible, and we are interested in that as well. Exactly like you mentioned, the core shell. So two things for batteries, a lot of people actually even have a post process to do some coating to passivate, not passivate, to enhance the stability of the material. And that step might be able to be incorporated with this. And also, like Sean has mentioned, in some applications, you might not want to have a uniform distribution of things. You might want to have a gradient or even a solid shell and a core. So the concept we want to demonstrate here is that controlling the process is really important. And there are tools or knobs we can turn to change the distribution of things rather than purely relying on the physical diffusion process.
Yeah, so, just to follow up with that. So the whole lithium shell thing, is that a thing, do you know if that's unique to lithium specifically, or is that a thing that happens with other particles that you ever tried?
Yeah, so the quick answer is that we have not tried other particles, but for lithium, I could expect that because lithium element is lighter than other transition metals.
Okay, so
meaning that
it's
the diffusivity is bigger, right? So it goes out. It definitely depends on the physical properties of the salt.
Okay, thank you.
All right, so I still see quite many questions, but unfortunately we already passed 12. So to avoid interference with other schedules, let's close the session here. So I also wrote down the names, so maybe we can have some more email conversation after the meeting. So thank you again, Dr. Deng, and thank you all for joining the seminar.
Thank you all for the questions. Feel free to follow up via email. I'd be happy to have further discussions.
Great, thank you.
Nice meeting you all.
Bye.